Um, Hello, everyone. Sorry for a bit of a rocky start, but I appreciate everyone waiting outside while we got the room issues sorted. Welcome to quarter two of Santa Cruz Artificial Intelligence. I'm glad you guys could all make it. And just in general, this quarter, we're going to be jumping in to a little bit more of neural network stuff. So machine learning, deep learning, neural networks, all stuff that we've kind of heard talked about, but maybe don't really know what it means. In the previous ones, we've been doing more artificial intelligence, just generally what kind of algorithms, models are out there. But now we're going to start diving into what we kind of mean when we talk about artificial intelligence and machine learning in the modern day. And that's why we're going to be starting with Introduction to Neural Networks. But first, we've got a small announcement. Well, big announcement.
Yeah, we're excited to talk today about what we have. Next slide. We have SkyJam. Yes. Our one-time competition, in addition to our normal Sky's No Limit competition, we are hosting SkyJam, which is approximately 4 hour. You can think of it like a hackathon where it's a competition between you and other students who are participating to program something. We're not going to say what, but there's a theme and there's lots of money for prizes. It's very exciting. We're really hoping to put on a great event. It's going to be, right now it's scheduled for January 26th at 3 p.m. We hope to see you all there. It will be in this room, E2-180. Yeah, we'll be announcing more info soon, so keep an eye out.
Okay, so now to get into like what we're actually going to talk about today. So today is going to be, like Kevin said, it's going to be an introduction to neural networks. So first we're going to talk about the different components of a neural network. So that would include something called a forward pass. And we're going to do an introduction to something called gradient descent and backpropagation. But this aspect we will go into more detail for next week. So today we just give a brief overview of what that is at a high level, just so next week it's not completely new. So we'll also go over some terms in neural networks and how we'll be referring, which are terms we'll be using going forward. We'll talk about what activation functions and loss functions are. So if you don't know what these are right now, we'll go over that. And so yeah, let's get into it. So firstly, what is a neural network? So the idea of a neural network is kind of inspired by the brain. And I'm not a biology major, so I don't know exactly these terms. But the idea is you have some neurons, some inputs go into these neurons, and they're sent through some channels, and then they're processed by another neuron, and you can get some output out of that. Again, I'm not a biology major, don't exactly know how the terms and stuff, but that's the idea. But in terms of like computer science, machine learning, what is a neural network? So you can think of a neural network as like a function machine. So you'll have some input, something will happen, and you'll get some output. And we're not here to say that something happens, so let's figure out what that something happens means. So this is a kind of relatively simple neural network. And we see that we have these circles that are outlined in red, and these circles are called neurons. But what exactly are these? Well, it's just some value. So this circle has some value. This circle has some value. This circle has some value. Every circle here has some value. And we just call that value a neuron. So we also have these columns. So you see this, these red circles, they form one column. These blue circles or blue neurons, they form another column. And this green one forms its own column. And we can split these into the, so we call this first layer or column. So each of these columns are called a layer. And we call this one the input layer. This final one, our output layer. And so what this means is our data, so what we're going to pass into the neural network comes into this input layer. And our output, or what we're going to get out of this neural network, comes in the output layer. And then we also have this middle hidden layer. And this is just in between the input and output. So all the values that get passed into our input get sent through the hidden layer. They're processed in this layer, and then they're sent to the output. So does this idea make sense so far? Okay. And then finally, you see these arrows over here that are kind of out bolded in red. So these arrows are called weights. And we see that every neuron, so every single neuron we see on this diagram is connected to the next layer, every neuron in the next layer by a weight. So if we look here, this neuron here, you see a connection to this neuron, you see a connection to that neuron, this neuron, just this neuron, etc. And the same thing here. And then if you look at this neuron, it's connected to this final neuron here, this neuron is connected to this, and so on and so forth. And the weights essentially tell us the importance of the connection. So if a weight has a very high value, we say that, so for example, if this weight right here has a very high value, we're going to say that the value at this neuron is very important to this neuron. So essentially, if a weight is connecting a neuron A to neuron B, we say that neuron A is very important to neuron B. Okay, so we know the different components of a neural network, but how does this work? How do we go from input to output? And that's where the idea of the forward pass is. So essentially, the forward pass is how we're going to go from our input to our output. So let's kind of demo this with a simple neural network. So here, just to bring back some of the terms, in our input layer, we have 2 neurons. In our hidden layer, we have 1 neuron. And in our output layer, we have 1 neuron. And we're going to call these the input values D1 and D2 for data point 1, data point 2. And then every neuron has a weight associated with a neuron that it's connected to. So this neuron is connected to this neuron, and it's associated by some weight. We call it weight 1. And this one is for weight 2. And this neuron is connected to this final neuron by weight. We call it weight 3. So right now, this comes from our data set. So we know these values. We don't need to derive these in some other way. We know what these values are, and we're calling them D1 and D2. But if we want to go from our input to our output, so if we want to find this value right here, first we'll need to find this value. And how are we going to do that? Well, we have our data point. We have some importance connection. We have another data point. We have an importance connection. And so what we're going to do is we're just going to multiply this value, the value at the first neuron by this weight. And then we're going to do the second neuron by its weight connection. We're going to sum the two together. And then we're going to add on a small bias term. And this bias term will go into more detail a bit later. But essentially, the general idea is we're going to take every neuron in the current layer. So this is our current layer right now. We're going to take every neuron and we're going to multiply the value at the neuron by the weight with the final neuron that we want to calculate. So we want to calculate H1. So we're going to take D1 and multiply that value by its connection with H1, and D2 multiplied by its connection with H1. Add the two together and add a small bias. Does that make sense, Evan? Any questions? Okay. And now if you want to calculate O1, remember, we want to get to our output. So right now, we just have the value at H1. And our goal is to get to the output. So we have to do this again. So you have to go through this process one more time. So now, repeating the same process, we're going to take, this is now our current layer, and this is the layer that we want to evaluate. So we're going to take whatever we know in our current layer. So we're going to take the value in our current layer. In this case, it's H1. We're going to multiply it by its connection with the neuron we want to evaluate. That's O1. And then we're going to add a small bias. So this final calculation would be H1 times weight 3 plus some bias equals this final neuron. And so now we've taken the input values and we started at the input values and we have a final output value. Does everyone understand how this works? Any questions so far? Okay. So we just did this for one neuron. So we took the input, we use it to calculate one neuron, and then we use that to calculate this final output neuron. But when we actually in a full neural network, we're going to have more than just one neuron in our hidden layer. So in this case, we have 6, but we're going to have more than one essentially. And that exact process, we're just going to repeat it for every layer in our every neuron in that next layer. So if you want to calculate this layer, we're just going to repeat that process. This value times weight plus value times weight plus some bias for this neuron, and then do it for this neuron, this one, this one, this one, this one, and then repeat that same process to calculate the output. So again, it would be like the value at this neuron times this weight right here, plus the value at this neuron plus this weight, and for the rest of them as well. So let's just kind of demo this with some real numbers. So here's I've labeled a neural network with some weights that I've put in, some input values, and some biases. And let's just start by evaluating this first neuron right here. So we're going to say that our input value has a value of 2 for the first neuron, and for the second neuron we have a value of 4. And this weight connection, we're trying to evaluate this neuron right here. So the weight between this first neuron and this hidden layer neuron is 0.5, and the weight between the second one and this first neuron is 0.2. So using the process that we did in the previous slides, can someone tell me kind of explain to me the formula for how we would go about calculating the value here? Yeah. Okay, so 2 times 0.5. You're almost there. So remember we said we'd take every neuron in this first layer. So you took this one and multiplied it by its weight, so that's right. But now we also have to account for the other neuron. So how would you kind of adjust your answer based on that? Exactly. Yeah. So based on that, it would be 2 times 0.5 plus 4 times 0.25, and then plus this bias term, which you pointed out. And then if we evaluate that fully, we get the value of 3. Okay, so what about this one? Does someone else or anyone want to try the second one? So now we're evaluating this neuron, and we have same inputs, but different weights. Does anyone want to try? Yeah. Exactly. Good job. So like you said, 2 times 1 plus 4 times 1.5 plus 2, and we get 10. And just for the sake of time, I'm going to skip this example. And I've gone through, on the slides, I just filled in the rest of the values. You also have access to these slides. So if you want to practice, do the answers, check your work, you can also go about that. And so, okay, now we have all the values for our hidden layer. And again, we don't want to stop here because we want an output. So now we're going to take all these values and repeat the same process going to the output. So does someone want to, you don't need to give the exact answer, but just the formula for how you would calculate that. Does anyone want to try this one? It's the exact same process. So we're going to take every neuron in this layer, and because we want to find this neuron right here. So we're going to take every value, multiply each value by its respective weight, and then we're going to add on this bias term. So does anyone want to try? Yeah. Oh, this one. Okay, that's a good question. So are you talking about going from, like, when we're at this kind of these stages, or when we're trying to go from? So that's close. So remember, if we're trying to calculate this this value here, we want to look at all the values in the previous layer. So we don't just want to look at one particular neuron. We want to do this process of neuron times weight, but we want to do that product for every neuron and its respective weight, and then add them together. So remember how here we did we did 2 times 0.5 because we were trying to find this neuron here. So we did this input value times this weight right here, because this neuron is connected to this neuron by this weight here. And then because we have to repeat that for every neuron in this input layer, we took the second neuron, which had a value of 4, and we found that this neuron is connected to this neuron over here by this weight, which is 0.25. And that's why we took the product of both of those, right? I mean, sorry, like we did 2 times 0.5 and then 4 times 0.25, and then we added them together, right? Yeah, so we did this process. And then we added on the bias. So if we're going to go, exactly. So exactly. So that's exactly what you said. We do 3 times 1, 10 times 1 was 0.1, 1 times 0.5, negative 4 times 1, 5 times 0.2, and 2 times 0.5. And then at the very end, we add the bias. So we don't add the bias to each of these terms. We first do that like neuron weight combination or multiplication. After we do that for all the neurons and we add all those sums together, at the very end, we add that bias. So does that clarify for everyone?
Is you can just follow the arrows. So if you're trying to calculate a given node, it's all of the arrows going into it are what you use to calculate it. And when you calculate an arrow, you just do the node that it's coming from times the weight of the arrow.
Yeah. Okay, so just to recap, so far we've covered the forward pass. And the idea of the forward pass is to help us go from our input to our output. And the way that we do that is if we want to calculate, say, this neuron here, we would look at every neuron in the layer prior to it. We'd take the value at that neuron and we'd find the weight between that neuron and this neuron that we want to evaluate. So as Kevin pointed out, if you have this diagram, you can think of it like the node and then follow the arrow between this node and the node you want to evaluate, and then multiply that weight that you followed times the node value. Repeat that process for the second neuron, and if you had more neurons, you would also repeat for those ones. Sum them, add them all together, and then add that final bias term. Okay, so right now we have just been looking at this diagram, and we've been doing all our calculations based on this diagram. And we've been looking at one neuron at a time and saying, okay, how can we evaluate this one neuron? But if we have to do this in code, that's going to get longer and messier. So there has to be some way that we can easily represent all these weights and neurons and everything. There has to be some simple way to represent this. And the answer to that is matrices. So I've taken all these weights. I'm just going to focus on this part of the neural network right now. And I took all of these weights and I put them into a matrix. But you might be wondering, okay, how did we go from this like list of numbers or column of numbers to a matrix? And we can think of it just by looking at, so if you look at this matrix, you see that we have 6 rows, right? And over here, this is the layer we want to evaluate. And we see we have 6 neurons. So we have 6 rows, 1, 2, 3, 4, 5, 6, and 6 neurons. So we can say that every row in this matrix represents a neuron in what we're trying to calculate. So this is a neuron, this is neuron 1, so this is this neuron. this row is this neuron, this row is this neuron, this row is this one, and so forth. And if you just look at these two, so this third column I'll come to in a bit, but if you just look at these two, you see that we have right now 2 columns and we have 2 inputs. So we can say that the rows that represent this layer that we're trying to calculate, and the columns represent the inputs that we have. And also, if you look at this, so if we look at column 1 and row 1, and we say that columns refer to inputs, so this would be input neuron 1, and rows refer to the outputs that we're trying to calculate. So if we look at column 1 and row 1, that would be 0.5. And if you look at this first neuron and this first output neuron that we're trying to calculate, we see that this weight is 0.5. So we can say that the connection between this graph or this diagram here and this weight matrix is that the columns, the value at a column and row represents the weight between that column's neuron and the row's output neuron. And that might have sounded a bit confusing. So I'm just going to go through this and show you what I mean. So again, we see this 0.5 is at column 1, row 1, right? So that means this 0.5 is associated somehow with this final neuron, this output neuron here. And since it's at column 1, we're going to say that we're going to look at this neuron, this first neuron, and we see that this weight is 0.5. And then if we go 1 column over, so if we look at the second neuron, now the second neuron's connection with this output neuron is 0.25. And we see a 0.25 right here. If we look at the next row, so the next neuron in the output, so this will be the second neuron, which corresponds to this row, we see that this first neuron's connection with the second neuron has a value of 1. And we see a 1 right here. And then the second neuron's connection with this the second output neuron has a value of 1.5, which we see here. So does anyone have any questions on that mapping so far? Okay. And okay, so now if we look at this column here and we look at all our biases, does anyone see any similarities between this column and our biases? So we have a 1 over here and a 1 over here, a 2 and a 2, a 1 and a 1. So does anyone see any similarities between the two? They're the exact same. So this column is essentially our bias values. So the bias value for our output neuron 1 is 1. So we had a 1 in row 1. In row 2, that bias was 2. So, or neuron 2, the bias was 2. So we have a 2 in row 2. In row 3, we have a 1, and we see third neuron has a bias of 1. And if we go down, we see that mapping. So 1 here, 2 here, 2 here, -2, -2. So when we were doing this whole process of evaluating the neurons, we were essentially multiplying value by weight, next value by its weight, and adding them together, adding a bias. So that essentially means that we have these weights, but we can't use them alone. So we have to relate them to our input in some way. And so the way we can kind of simplify this is by saying, to calculate our next layer, we want to take our weights and multiply by our input. So right now I've created an input matrix called D, and we see that it has 2 rows. So this first row corresponds to this first neuron. We see this first neuron has a value of 2, and the second row corresponds to the second neuron, which has a value of 4. So does this idea of weight mapping and this input mapping the input values into matrices, does anyone have any questions on that? Okay. So to get to our next layer, remember, because this whole time we were just doing value times weight plus value times weight plus value times weight. So the way we can relate this weight and these inputs is just by multiplying them together. And if we actually try to do this multiplication, we see we're going to do, just by the rules of matrix multiplication, we're going to do this value right here times this value here plus this value here times this value here. And now we have to, what about this value? Now we don't have anything to multiply this by. So for that exact reason, we actually need to kind of extend our input matrix to have a 1. And the reason is because remember when we're multiplying matrices, we do, we're taking this column, this value right here, multiplying it here, this value here, multiplying it here. And because we need to do something with this bias value. And so on. So like at this point, we were adding on the bias value. But if I have a number and I just want to add it on, I can say I'll multiply it by 1 and then I'll add it. So if I have 3 plus 2, I can say it's not different from me doing 3 plus 2 times 1. So that's exactly what I'm doing here. I'm adding this 1 just so I can add the bias value when I do the math. So when I add this 1, now I can just do 0.5 times 2 plus 0.25 times 4 plus 1 times 1. Does that make sense for everyone? Okay. And then I just went ahead and done the calculations. And then if you want to practice with this, you have the slides and you can check your work. Okay, so this is, we can see that this is actually not that different from when we were doing with the matrices versus when we're doing on this diagram. It's actually not that different. So earlier we were taking, remember we were doing input times weight plus next input times weight, adding a bias. So we got 2 times 0.5 plus 4 times 0.25 plus 1. And that's also what we were doing here, right? 0.5 times 2, 0.25 times 4, 1 times 1. So we're doing the exact same process. We're just representing it in a different way. So up until now, does anyone have any questions so far? Okay, so far we had this neural network. So we had 1 input layer, 1 hidden layer, and 1 output layer. But really, we'd actually have multiple, in more complex neural networks, you'll have multiple hidden layers. So right now we just had 1, but really how it would look like is you'd have an input layer, output layer, so that would stay the same. That concept would stay the same. And then we'd have 1 hidden layer connected to another. So again, the math, everything stays the same. We're still doing neuron value times weight plus next neuron times weight plus next neuron times weight plus next neuron times weight, add the bias, get this value. That process is the same. It's just that we have more layers now. And we'll expand more on this next week. So this is just kind of, so you have an idea of what it looks like. And so we've gone over like how to use a neural network, the forward pass, but why exactly do we need a neural network? Like why isn't what we've done before good enough? And so let's look at this data set. So let's say I want to fit a model to this data. If I try to fit this line, is it a good fit to the data, would you say? I mean, it's not horrible, but what if we tried this? Would you say this is better or worse? It's definitely better, right? You can see all these nodes are a lot closer to the line. And so to make this kind of curve is what neural networks are for. But how? We've just been adding and multiplying numbers. How does that actually work? And so that comes to the idea of activation functions. So these are just some common activation functions, but essentially an activation function is nothing but a function. So remember, a function takes in a value and spits out another value. And that's what an activation function does. It's going to take in some value and it's going to output another value. And the main purpose of having this activation function is to introduce some nonlinearity. So if you look at each of these, like it's not a linear, it's not a straight line or diagonal line. There's some curve aspect to it. Like, okay, yeah, we see here, this is a straight line, but also notice that this cuts off here at 0. So there's in all of these functions, the commonality is that there's some sort of nonlinearity in the graph. So if I have a graph y equals x, and I take my input, I take x values 0 through 20, and I plot them on the line, I'm just going to get a diagonal line going from 0 till 20. So I'm not going to get anything fancy out of that. On the other hand, if I take x squared and I plot the line 0 through 20, I'm going to get a curve. I'm going to get some sort of curve. I'm not going to get a straight line. And the same thing here. If I take another function, say tan age, and I take a series of x values and plot it, I'm going to get some sort of curve. So until now, like at this point, we said that the way we represent in math how to get the next layer is to do the weights between the two layers. So if we're trying to go this layer to this layer, it'd be the weights between these layers times our input data, or like the values in the layer that we're starting at. But now we can change that and say we're actually going to apply whatever we get. We're going to pass whatever we get through an activation function. And all this is remember we got some values for these for these hidden neurons. And so each of these values, we're just going to take it in and we're going to pass it to an activation function. So if I got the value 3 here and my activation function was x squared, now that value is going to be 9. If I got 4 here, that value is going to be 16. If my activation function was x squared. So again, these are just some of the common activation functions. You don't need to memorize this. This is just out there for you if you want to kind of explore some of these. And so just to recap, right now we have we've explored the idea of forward pass. So that's to go from your input to output. And it's essentially multiplying the weights between two layers times the input to that first layer. And then applying all of those, everything you got from that multiplication, putting all those values into an activation function. And an activation function is just another function. And the purpose is so that we can introduce nonlinearities. So we can kind of go from a fit that's this kind of line to something that's has more curves. And now we're going to kind of touch on the idea of backpropagation. This will be extremely high level, very general. And we'll go into a lot more detail with this next week. But now, so up till now, we were working with some weights. But where did we get those weights from? So this input layer, we got it from our data. But what about this? Where did all these come from? And I made those up. But in reality, when you're actually starting with a model, you're going to be starting with initially random weights. And the purpose, your job is to train it. So initially, it's going to be some set of weights. And you're going to put in some data. So I'm going to say, okay, like I studied for 2 hours, I slept for 4 hours, and now tell me if I'm going to pass or fail. And then, the model might be wrong. It might say, oh, you're going to pass, but in reality, I'm going to fail. So our job is to train it so that we can find the weights that help our model perform optimally. So how do we train this model? One aspect of this is the loss function. And this is just a function that can help our model find out how wrong it is. And we'll go into more detail with this next week as well. And the second one is backpropagation, which is essentially how do I fix that? I know how wrong I am. Now, how do I fix that? And backpropagation uses gradient descent. So again, these are all just terms. We'll go into more detail of this next week. This is just a high-level overview. And essentially, that is just updating the weights and biases. And our goal is to find the weights that minimize the loss, or you can say helps our model perform very optimally. Here are some common loss functions. Again, you don't need to memorize this. This is just if you want to kind of get an idea of what a loss function is. Again, it's just a function. And okay, finally, just to recap, we've gone over the idea of forward propagation or forward pass. So to get the values in our next layer, we want to take the weights between the layer times the input and apply an activation function to it. The purpose of an activation function is to introduce nonlinearities, and to train our model, we use backpropagation, which uses loss functions and gradient descent to find optimal weights and biases. And this aspect, if you don't fully understand it, it's okay. We'll go into more detail next week.
Just one thing I wanted to mention is this forward propagation is half of neural networks. The other, maybe it's 2/3. The other little bit is back propagation, which we slightly touched on. And next week, we're actually going to go into what's a loss function, how does this back propagation actually work, et cetera, et cetera, et cetera. But this is half of neural networks. You guys just learned what half of neural networks are. That is really incredible. Everyone, neural networks is something that's talked about a lot. And now you guys learned half of what these things are, how they work. So there is a collab if people want to check it out on their own time. Unfortunately, the meeting's just about over. But we also might go over it next meeting instead. But yeah, so that's all. Thank you guys so much for coming. This is our Discord and our link tree with all of our other socials. If you have time and would like to fill out the feedback form, that would be much appreciated. And yeah, we'll see you guys next week. Thank you so much for showing up. Cool. Sorry.
How do you turn this off?
It's just at the bottom.